The goal of this space mission is to design a nanosatellite to close an environmental artificial ecosystem able to maintain alive and retrieve data from a colony of Roscoff worms. With this goal, a satellite is pre-designed with the following subsystems: Mission Analysis and Launcher, Attitude, Determination and Control, Communication and Ground Segment, Thermal Control, Configuration, and Electric Power.
In order to present this preliminary design proposal, some existing missions have been studied. GOMX-3 is a 3U CubeSat deployed from the International Space Station. All components used in this mission, ComSpace components, are ISS launch compliant. Since our satellite is also deployed from the ISS, these costs were prioritized in order to avoid additional tests required on non-ISS launch compliant components. Ryko mission is a 2U CubeSat with our same orbit. Our de-orbiting mechanism is based on the one demonstrated in this mission. CubeLab is a 1U standardized CubeSat for verification of space-relevant technologies. A CPV system, which is proposed as a design option in the innovation section, was one of the main payloads for STEP mission. OFT-Next NanoSat is a LEO 6E CubeSat with the same size and similar data handling requirements. Our OBC choice was based on the proposal. CubeNet mission is composed of two low-cost Observer 3U CubeSats located in LEO and a third 6E CubeSat containing a 2 kg meteorite, also deployed from the ISS and with similar communication requirements.
For mission analysis, we started by selecting the optimal orbit, in this case optimizing for lower cost. Due to this, it was decided to launch the satellite from the International Space Station, which gives us an orbit equivalent to that of the ISS. With this orbit, several simulations were carried out in software such as IMAC, all of which demonstrated that they were capable of meeting the requirements of the mission. Finally, it has been considered to add a down-deorbitation device, which allows us to accelerate this process to only 9 days from the end of the scientific mission to avoid generating space debris. The scientific payload will be formed by an L-shaped structure of size 3U. Due to the configuration of the 6U satellite, this payload will occupy 3U in L next to one of the sides of the satellite, leaving on the other side another space in the L form to locate all the necessary subsystems. Therefore, next to the payload will be devices such as batteries, OBCs, EPS, traction wheels, or communications. Each of these subsystems will have its own temperature and power requirements, and compliance with these requirements must be ensured, establishing the strictest temperature range and the highest power consumption.
Moving on to the Attitude Determination and Control subsystem, we are going to take a closer look into the requirements and purchasing choices for this subsystem. Given the restrictive requirement of 0.5 degrees error in naming, we have selected an attitude determination instrument for both eclipse and no eclipse modes. During eclipse mode, a GPS device determines both position and attitude of the spacecraft, using extra power from the batteries. During non-eclipse mode, attitude is going to be determined by 6 solar sensors, placed one on each spacecraft's faces. Each sun sensor measures the angle in which solar radiation incides its face, giving enough data to the ATCS OBC to determine with enough precision the data required. Now, speaking of that, our configuration includes an OBC dedicated to ATCS that is connected to all the elements through a motherboard compatible with all components. For the actuators, we first need to measure the amount of torque we'll be needing. Starting with disturbance torque, which needs to be compensated, we estimated a magnitude order of 10 raised to minus 23 generated by gravity gradient, 10 raised to minus 9 produced by solar radiation, and 10 raised to minus 6 due to Earth's magnetic field. Gravity torque can be considered negligible at 400 attitude orbit. Now, proceeding to slew maneuver requirements and considering the maximum torque the payload can endure, we calculate a torque requirement of 0.8 mN. Comparing the magnitude orders, this is the most restrictive one, so we have selected a component that offers 1.5 mN torque, consisting in 4 inertial wheels in pyramid configuration. This component also accomplishes the 0.5 pointing allowed error.
In the line of the present systems analysis, different code surface units have been analyzed. The selected unit is the nanoMUSE A3200. As you can see, it has a 32-bit processor and a heritage of 5 years. It is designed to be housed adjacent to the GPS together with the NanoDock ADCS6.
Time to move to communications. The whole system in both the ground stations and the satellite communication subsystem, which includes the radio and the satellite equipped antenna. For this mission, an S-band transmission has been selected for continuous communication with Earth. About the ground station network is strongly restricted by the orbit parameters. For our profile, the ground antennas that will receive our transmission from space are nanoMUSE, located on West Australia with an antenna diameter of 35 meters, Kourou, the familiar European Space Agency ground station located on French Guiana with an antenna of 15 meters, which will be our operation center, and Redo, located in Belgium, Europe, with a diameter of 15 meters. Together with an elevation angle of 16 degrees choose for safety reasons, will provide nanoMUSE satellite a total link time coverage of 2,254 seconds with an antenna almost symmetric reception gain of 48 decibels. Now let's move on the satellite communication subsystem, which is a configuration of two GOM-space antennas with a beam width of 70 degrees and a transmission gain of 8 decibels, located at the Earth-oriented satellite phase. For the radio, we select a configuration of two redundant modems with an internal solid-state memory of 32 GB for what could happen in the space. Our calculated transmission data rate must be at least 1956 kilobits per second in order to have the capability to transmit the information without using the memory budget, as exposed on the NANOSTAR requirements. This means the radio software will be taken to its maximum performance level. Considering the data rate and the system limitations, the link is defined with a pointing loss of 0.1 decibels and a space loss of 156 decibels and a coverage noise temperature of 27 decibels Kelvin. Finally, the link margin solved for the system is 2.22 decibels, which makes nanoMUSE satellite capable to speak with Earth.
In this section, we will discuss the power consumption, power generation and storage of the platform. The first step in power estimation is to determine the satellite's different operational modes. These are defined as 4 different scenarios during the satellite's operation that not only define the required behavior of the satellite and attitude, but determine which of the active subsystems need to be functional at each point. The first operational mode refers to the generation of power using the satellite's solar arrays. This mode is entered in the illumination conditions, that is, not during eclipse. The second operational mode refers to satellite communications with the ground station. This mode is entered when performing a pass over the ground stations. This can happen either during illumination or eclipse. The third operational mode concerns the acquisition of data by the imaging system, so in this case the payload is operational. The last operational mode is entered when none of the previously described conditions are given. This happens when the satellite is in eclipse and both the payload and communications are idle. With the different operational modes well defined for the mission, an estimation of the power budget can be performed. This analysis provides the information needed for solar array sizing. Solar panels will need to provide 33.9 watts to meet power requirements of the loads. This translates into a 12U area of solar arrays. The proposed configuration includes solar panels attached to the X phase of the satellite and deployable 3U solar panels in phase Y. This adds up to a flat surface of 12Us. The sun pointing orientation of the satellite will allow these arrays to be optimally facing the sun in the power generation operational mode. The selected solar panels and the power generation capabilities are displayed in the following tables. During eclipses, power is supplied by a battery pack. This battery is sized accordingly to the most restrictive scenario, an orbit with data acquisition and a communication pass during eclipse. Using a 30% depth of discharge, the required battery capacity is 37.1 watts-hour. For this purpose, the NanoPower BP4 quad battery pack is selected, consisting of 4 lithium-ion cells with a total capacity of 38.5 watts-hour. The following figure shows the evolution of the battery capacity along the most demanding scenario. As you can see, the depth of discharge does not exceed 30%. To complement the battery selection, the GOM-space NanoPower P31 power supply has been chosen for the best compatibility and ease of integration. This EPS features regulated 3.3 volt and 5 volt power with 6 independent switchable latch-up protected outputs. The following table shows the selected batteries and EPS solution.
The satellite configuration will be shown in more detail in the report. As a brief summary, a 6U configuration has been chosen. This configuration allows us to host all the devices inside it along with the payload. Outside will be a configuration of solar panels with 12U aligned with the sun thanks to 2 deployable panels in 3U. Other 10U panels perpendicular to the sun will give us extra power during orientation maneuvers to transmit data to the ground. The antennas and the MLI will be located on the opposite side to the sun.
Regarding thermal control, it has been analyzed 2 opposite cases. On the one hand, the cold case in total eclipse and no heat from the sun. On the other hand, the hot case with direct incidence of the sun. As the most restrictive subsystem were the batteries, with a temperature range from -20 degrees Celsius to 40 degrees Celsius, the whole satellite has been designed according to it. For the cold case, a small polyimide heater for 3.5 watts was needed, and for the hot case we have used a multi-layer insulation. For the launch system, we have chosen a CubeSat deployer at the ISS to deliver our satellite into orbit. NanoRacks, which is the company's name, is in charge of every process, from integrating the satellite into the module, storing bubble wrap and foam to avoid any damage, to the deliver at the ISS and its deployment. Once the satellite is ready to be deployed, the front doors of the module will open and the CubeSat will be released. Thanks to it, the cost and complexity of the launch system has been reduced.
Relating organization and timeline, during the first stage of the project we settled a Gantt diagram. You can see the different phases of the project on screen, overlapping over time. Please notice the weekly meetings that took place over the entire duration of the project, which serve for organization purposes given the current state of the project.
An additional study could be to predict and test power generation enhancement with the CPV system. CPV system is a photovoltaic power system that can enhance the power generation performance of a solar panel by concentrating and illuminating using the Fresnel lens system installed on the edge of the solar panel, even under the worst condition of incidence angle between the solar panel and sun, as shown in the following figure. The commercial Fresnel lens system made by polymethyl methacrylate could be installed on the plus set and minus set solar panels, thus allowing for a certain amount of power generation. Scientists from Tokyo University of Science developed a high-performance and compact OBC for micro and nano satellites using commercial off-the-shelf components, including a structure to share software and enhance reusability. This system has the potential to be a powerful piece of educational equipment. A high level of technology is necessary for the development of small satellites for educational purposes today. However, the difficulty is reduced by using the proposed onboard computer system and allows more people to participate in satellite project. Perfect software compatibility is achieved using the Hodoyoshi SDK software framework that is compatible with the silicon on insulator system on a chip. The specifications for the proposed OBC are described in the following table.